Now we'll talk about the what and the why of normal distribution, but before that we need to understand what a normal distribution is basically. Whenever we can see that data is flowing out of a natural process and the data is also voluminous, that's where we say that the data typically follows a normal distribution. Now, if you look at the characteristics of a normal distribution, it's like an inverted bell curve, that's what we can say. And the processes through which a normally distributed data might come out might depend. Say, for example, if you're tossing a coin, say, which has binary output as true or false, and you keep on tossing this coin again and again, that is called as a Bernoulli trial. And when we say that it's a Bernoulli trial, it basically gives a binomial distribution, which if we take to a large scale data, turns out to be a normally distributed data. Now, normal distribution is also called as a Gaussian distribution, right? So there's an example which is shown over here, but typically what we really have to understand is that a normally distributed data has a very strange characteristic. The characteristic is that the mean is equal to the median is equal to the mode of the data, right? So typically all the statistics, mean, median as well as mode, would end up as the same data point. That is what is normal distribution. And why do we need to understand normal distribution is because if we understand normal distribution, we have some set of hypothesis which says that typically data would be spread between these limits. Now we need to rewind back and remember that we had done something called as measures of central tendency and measures of dispersion. Measures of central tendency related towards like mean, median, mode, which talked about where is the data located centrally, right? Where is the concentration of bulk of data. And measures of dispersion, that is the standard deviation, basically spoke about how far off can we see the data spread, right? So if we look from that perspective, we know that sigma is standard deviation, and if I have a normal distribution, I can say that with relation to the mu, which is the population mean, a mu minus 1 sigma and a mu plus 1 sigma, right? So two limits on both the sides of the data, as you can see on the screen, is basically talking about like 66% of the data is concentrated in this area. If you go between mu minus 2 sigma and mu plus 2 sigma, that's where you can say roughly 95% of the data is concentrated, and between mu minus 3 sigma and mu plus 3 sigma, you can say 99% of the data is kept, and anything which goes really beyond this would be treated as an outlier data, right? That's basically what we talk about normal distribution. So now you can see on the screen that's a 68, 95, 99.7 rule. Now these things might keep on changing basis various documentation. So in some statistical books you might see 66%, somewhere it might be 68.27%. Very pertinent. What document you have got on the screen right now is talking about very specific things, but you can always give the rule of 65, 95 and 99 to be roughly correct, right? So that's what we spoke in the previous slide. Now, if you remember something like skewness and kurtosis, which we spoke long time back, right? So that if it comes to picture, you can say you can see there is three distributions shown on the screen, right? So there is one which shows a very picket distribution, and you can see roughly the mean is distributed around -4, and the sigma, that is standard deviation, is 0.5. And in the next phase you can see that it's centered around 0 and the standard deviation is 1.5, and as you go towards the right, the mean becomes 3 and the standard deviation is 1, right? So what is happening is that the data is getting spread as you go from a standard deviation of 0.5 to 1.5, and again when you come back to 1, it starts to look more similar to a normal distribution, right? Now, why do we really try to understand all these things is because based on this you can make inferences, right? So if you know that it's a normal distribution, you can surely say that, okay, if I compute some statistics out of that, that would be something like this. Now, one more important aspect is z-score of an observation. Now, whenever data is raw, if you want to make inferences, say for example I have something like rental values of properties in Kandivali and rental values of property in Borivali, and both of them have a mean value, and as a researcher I am really interested in understanding whether a 2 BHK costs a different price in Borivali versus Kandivali. In that case I might challenge the status quo statement that they are equal and say they are not equal, and do some sample data collection and then try to test them. But what really makes it important is that are we standardizing the data, right? So are we really looking at how the data is standardized? So what we do is we create a z-score wherein you first collect the rental values, subtract that with the mean values divided by the standard deviation, and convert it to a standardized normal distribution. And then when we do the comparison, it really makes sense. So really doesn't make sense comparing an apple to an orange. So first get it converted to the same form and then convert it, check it and reason it, and then take an inference. And that is what is inferential statistics all about, right? So hypothesis testing, a very important aspect. So we do hypothesis testing every day. You wake up every morning assuming that there is land underneath your feet. So you put down your right or your left feet outside your bed and you assume that there will be land underneath your feet. That's a hypothesis which has been formed over a period of time whenever you have experienced this event, right? So that is a hypothesis, a null hypothesis, a status quo statement, which might not be possible sometimes, or you might have to accept the alternate hypothesis. Then you wake up, there's no land underneath your feet. So why is it important? From a statistical notion, it's important because you usually keep something which is a null statement or a status quo statement, like there's really nothing happening in the data, as a null statement. And the alternate hypothesis is that there is something which is happening, right? So that's about hypothesis testing. So you have two important aspects when you're formulating a hypothesis. One is a null statement and an alternate statement, called as null hypothesis or alternate hypothesis. And you typically find some notations like an H0 for a null and an H1 for an alternate. Obviously there are other documents also, or some kind of books in which the H1 might be shown as an HA, where A stands as an abbreviation for alternate hypothesis, right? So again, based on the kind of test, the kind of comparison. So usually when you're doing hypothesis testing, it will be an equality versus inequality statement test. If that is the case, you will have a two-tailed test, because you really don't know which side of the tail are you testing. But if it is something like greater than, which is tested in the null, and the alternate is testing the opposite of that, then surely you know that the alternate statement is going on the opposite direction, and that is why it is a one-tailed test. And based on the data, you can have right-tailed and a left-tailed test. Now, population sample, we have already spoken about this as to why do we take out samples from data. So usually hypothesis testing is done to basically infer that the sample which you have taken from the data, is it a correct representative of the population, and if it is so, can we take inferences out of the sample to be really applicable on the population. And that is why hypothesis statement becomes a base for all of this. Standard error and confidence interval. Now, standard error is the standard deviation of the sampling distribution. So basically, if you follow the central limit theorem, which basically talks about extracting data again and again from the same population and computing the mean, and then seeing at the distribution of these mean values, wherein you can make a statement that if the distribution is coming out of a normally distributed data, then this distribution also should typically follow a normal distribution, right? And based on that, you take estimates. So when you see some deviations which are coming from actuals, that is what is called as standard errors when you look from the central limit theorem perspective. So a sample standard deviation, or an SE, is nothing but the standard deviation of the population divided by the root of the number of observations. That's how you will term it in terms of a formula. The confidence interval is nothing but the range within which the true population parameter is believed to be found true with a given level of confidence. And this is a very important aspect, because whenever you're doing linear regression and logistic regression, you typically make a statement before starting experiment that you are running this experiment with 95% confidence level, or 90% confidence, or with 99% confidence, and based on that your significance levels also change, and that has a very important aspect, that has a very important effect on whatever you take out from your analysis. For example, if you assume under standard conditions a 95% confidence level, then your significance level becomes 5%, which is nothing but the error which you're ready to make. So if the hypothesis you are framing is something like, okay, a customer will make payments on time, and the alternative is that he is not going to make payments on time, and you do the experiment with a 95% confidence interval, then obviously your significance is 5, which basically means that alpha, or significance level, is the probability of rejecting the null hypothesis, given that the null hypothesis is actually true. So you're giving the rate of error which you're ready to commit. That's what is the whole thing. Now, Talking from the same previous slide, the p-value is directly connected to the confidence interval. So if your confidence level is 0.95, your p-value will be 0.05. So the ratio is p, or alpha is nothing but 1 minus confidence interval. So if it is 1 minus 0.95, that turns out to be 0.05, right? So many times we take decision by looking at some output from SAS or R, but we really don't understand why we are saying that this variable is not significant or it's significant. But by just looking at the p-value, we say that if it is less than 0.05, it's good for us, we can keep that variable. But the real crux of the thing is that you should look at the confidence interval, right? If you have framed that the confidence level is 0.99, then your p-value becomes 0.01 and it's not the same, right? So accordingly, you'll have to take a decision when you are accepting a variable or rejecting a variable in your framework, right? So the p-value and the confidence interval are directly connected, right? Now, talking about this, we already spoke about the p, right? When you look at a grid of type 1 and type 2 error, the alpha, the p is nothing but alpha. It's the assumption that the null hypothesis is true, but your model is saying that it's not true, right? So if you can see on the screen over here, the decision reject and accept is shown on the left side, and on the top side the null hypothesis is true and the null hypothesis is false is mentioned. So when real data says that it's actually a true statement, that means, say for example over here you try to frame a sentence like, okay, and a person is innocent, that's a null hypothesis, create that as a framework, and the alternate hypothesis is that he is guilty, right? So if you relate to this table, it's saying that the null hypothesis is true, that means it's something which is coming out of data, right? And you are making a decision that no, it's not that way, it's opposite, right? So when the null hypothesis that the person is innocent is actually correct and your model, that is the decision which you're giving, is reject, that means you're rejecting the null hypothesis, which evidently comes out to be the type 1 error, and it's nothing but the p-value, and it's also called as the false positive. Why? Because the alternate hypothesis is the event. You usually try to analyze a rare event in data. You are not interested in understanding who is going to make payments on time. You're really interested in who is not going to make payment on time. You are never interested in understanding which employee will still work with you in the next 3 years, but you're really interested more in which employee is going to leave your company. You are never interested in understanding which customers are going to do transactions with you, but you are more interested in understanding which customer will stop doing transactions with you. So it's always about the rare event. That's life, right? We really are not interested in what happens normally, but we are more interested in understanding what will otherwise happen, right? So that's false positive, right? And similarly, you have type 2 errors, which is talking about false negative, wherein actually the data says that the null is false. That means in this specific case where we are talking, we are saying that the data says that he is actually guilty, but if I say, right, that he is not guilty, right, so you are again doing some error, right? So if you relate from this whole grid, and if you see that null hypothesis is false, which means that the alternate hypothesis is accepted, which is that this person is guilty, right? That's the reality in the data, but you are accepting the null, which is not correct, right? So that's a wrong classification again. So that's a type 2 error, that's false negative, right? So these are the two errors, but now this is very difficult to fight with. For example, it's like your mother and your wife. So if you listen to one, the other one gets angry. If you listen to your wife, your mother gets angry. If you listen to your mother, your wife gets angry. So you typically cannot keep both of them happy. So you'll have to take a decision as to which error you are ready to make. And that's all about type 1 and type 2 errors in a small nutshell. So when you're talking about this distribution over here, you can look at the p-value. So the area under the tails of the student's tree distribution, which becomes more specific when you're looking at linear regression models, is the area wherein the null is not accepted, or you can say the area which is marked as plain, right? This is the area wherein you can say that the edge 0 or the null statement is accepted. Beyond that, what you're seeing in the further tails is something wherein you can say that you have failed to accept the null hypothesis, and so you have to accept the alternate. So the alternate is really the statement which you want to more often prove, and that is where you're saying that yes, my hypothesis is justified, right? And similarly, if you look on the lower scale, it's nothing but the t. So what you're seeing as a scale, if you see on the bottom side, it is the t value. So the two straight lines over there with a minus and a plus on this side is nothing but a minus t alpha by 2 and a plus t alpha by 2, which typically for a 95% confidence level would have a value like 1.96 on the negative as well as the positive side. So that is the cutoff value. So based on that, you take a decision whether you have to accept or reject a null hypothesis. So now, how to pick a correct statistic? So when you see it continuous data, right, and you're trying to do some tests. Now this really comes more from market research analysis, right, and not more from analytics. So if you are more into market research, this is what will help you as to whether you're going to use parameterized versus non-parameterized test and all those things. So when you look at continuous data, if there are two groups, right, say for example, when you're doing a linear regression, you're basically trying to test against two groups, right, one which follows the H0 and one which goes against the H0. So in this case, you have two groups. So if these are unmatched, right, the two groups are unmatched, then you do a t-test. If it's matched data, then you do a paired t-test. When you look at data wherein there are more than two groups, right, in that case you will typically be using ANOVA only, right. For example, when you're looking at something like a logistic regression model and you're trying to basically see how is the variance of behavior in different data with relation to different blocks, in that case you will be doing a chi-square, which is nothing but an ANOVA test only, right. So you can see an unmatched will have an ANOVA, whereas for a matched it will be ANOVA with blocking. That means you will hold one as test and you will keep on changing the other parameters. Now when it comes to ordinal data, so similarly for the previous case, now in this case you have two groups and greater than two groups. So if it is two groups, then you will use an unmatched test like a Mann-Whitney U or a median test. If it is matched, then you will use the Wilcoxon matched pair or the sign rank test. If it is greater than two groups, then you will use the Kruskal-Wallis one-way ANOVA, and if it is matched, then you will use the Friedman two-way ANOVA test, right? So these are basic standard rules, and sometimes you might convert data from one form to another if it makes sense, but that depends upon your experience as you go forward. Right. Now for nominal data, so based on the two groups and greater than two groups, if it is a 2 by 2 table versus a 3 by 3 table, you have two options. So if it is an unmatched data, then you have the Fisher exact test, and if it is the matched one, then you have the McNamara test. And if it is unmatched, which we typically normally use, right,